Hey, welcome back, nerds. Today we're talking about sorting algorithms. We're going to be covering three algorithms today that are pretty widely known and useful both in actual code and for learning. So first we have bubble sort. For worst case and average case are big O of n squared, and the best case is big O of n. If you're kind of confused about this big O notation, watch the video I put out last week. It goes into detail how big O is calculated and what it means. So bubble sort, it's really easy to understand. It's like a really simple algorithm that's taught at like a base college level. It's not really used at all anymore. It's slow and it's kind of inefficient, but it's useful for teaching. So how exactly does it work? Well, the big O was n squared, so chances are we're doing a nested for loop, and in this case we are. We're making n minus 1 loops n times, where n is the size of an array. So you have the outer loop go from 0 to max, and you have the inner loop go from 0 to max minus 1. And as you go through into that inner loop, you're checking all the indexes. So you're checking at index 0, 1, and then 1, 2, and then 2, 3, and so on. And if the small index is bigger than the bigger index, then you swap the numbers. What that means is every loop, the biggest number will be guaranteed to be at the end, and all of the smaller numbers are pushed one closer to their destination. One simple way you can optimize this is you just ignore the last n elements for each new outer loop. And we'll kind of show that in the code, which is a good point. These things can kind of be hard to explain sometimes. Sometimes it can be hard to wrap your head around. So showing the code will hopefully make it a bit more easier to understand. If you're still struggling a bit, when we run the code, there's going to be visualization set that I've set up. So hopefully that'll help. Next we have insertion sort. Big O is the same as bubble sort. Worst and average case is n squared. Best case is n. Now this is pretty similar to bubble sort where it's doing those comparisons and moving things, but it works faster. And it's actually still used for small arrays and within some settings that we'll get into later. So how does it work? Well, let me talk about it like without going into detail. Really what it's doing is going through, grabbing each number and then moving it into the sorted list that it's creating. So say you've already looped through like 4 times, you grab the fifth number and you're moving it into that subarray of 4 numbers and you're placing it in. Hopefully that kind of makes sense. Let's get a little more technical. You're making m loops n times, where n is the size of array and m is how many loops you've done. So when in the inner loop, you're grabbing at index m and you're comparing it and moving it. So it's kind of like bubble sorting, but once you get to a point where you're not making a swap, you stop and then you move to the next loop. Next we have quicksort. This is a pretty good sorting algorithm. Worst case is n squared, but the average case is big O of n log n, with its best case being n. N log n, that's pretty fast. So, like I said, this is one of the better sorting algorithms. It's still used quite a bit today. And how it works before we go into detail is it uses a pivot to continuously split up the list into smaller sub lists. It's a divide and conquer algorithm. Actually, a lot of implementations of Quicksort will use insertion sort once the sublists get down to a certain size, because at a certain size, insertion sort actually is a little faster than Quicksort. Sometimes algorithms can be pretty complex. So how does it work? There's really 3 steps, and there's recursion going on. So you pick an element called pivot, and it can be any element. It can matter, but if you don't know how the list is going to be formatted, if it's going to be somewhat sorted or if it's going to be like reverse order or anything like that, it might as well be random. It doesn't matter, or just pick like the middle element or the end element. You go through, reorder all the elements, so every element smaller than a pivot comes before it and every element larger than a pivot comes after it. Once you do that, you know the pivot's in the right spot, and then you repeat recursively by calling the same method on the sublist for before the pivot and after a pivot, so it keeps shrinking how much work needs to be done each recursion. Okay, so let's get into code. Okay, so before we get into the sorting algorithms, so let's go over some basic stuff. Main thing is we have this swap method, and it just takes two indexes and just swaps them. And then we also have some printing stuff going on, and we're just doing that so you can visualize things. Obviously, that all part isn't necessary. So first into bubble sort, is really it's just those two for loops, and really you just need that if statement and then swap. So we're going through from 0 to max, and then we go through from 0 to max -1 to account for so we don't get out of bounds, and then -I. That way, each process we're knocking off one additional number we have to check. And then we're just checking x and x plus 1, and if they need to be swapped, we swap them. That's really it. And insertion sort, like I said, pretty similar, has for loops, two for loops. Goes from 0 to count -1, and then we're going from that m value I was talking about, where it's the outer loop placeholder +1, and it's going towards 0. And then we just check if that number and the number before it, if they need to be swapped. If so, swap them. Else, you want to break out of this and then go back up to this outer for loop. Next, we have quicksort, and because you need to do recursion for it, we have some extra methods here. It takes in the list and then left and right. So we have this check just to make sure when we get to the end, we're not just endlessly recalling it on just one element. And first of all, we need to get the pivot. So we're having left and right where it's 0 and max. And first of all, we have this slower version of quicksort that somewhat resembles bubble sort, where we pick a pivot where we're just picking the last number in the array. And then we're just looping through every number and checking if it's we're just looping through every number and checking if it needs to be moved, move it. But because we're only checking, or because we're swapping just I and J instead of anything more complex, it's kind of bubbling up, and then once we do that one loop, then we can move a pivot to the middle. A better way to do it is pretty similar at the beginning. We're still looping through and we're checking versus a pivot, but the difference is instead of just like bubbling it where it just compares it next to it, we start right next to the pivot and go down, so that way we're doing multiple checks to make sure we're doing the least amount of swaps as possible, because swapping is a little more expensive than checking. So, and for each of these, I just gave them a list of 10 random elements. Okay, first off is bubble sort. So you can see how it's comparing, and if it needs to swap it, swaps it, and if not, it just keeps going through. In the second iteration, doesn't need to check the last number. Third iteration doesn't need to check the last two, and so on. And one thing that would speed this up is holding on to a boolean, and here we didn't swap anything, and just keeping track of, hey, we didn't swap anything this process, it's sorted. But whatever. You get the idea of how bubble sort works. Next, insertion sort, as you can tell, a little quicker. It's not doing as many checks and moves. But like I was saying, we're grabbing this number, checking it, doesn't need to move, grabbing this number, we have to move it, and then we don't have to move it, and that's how it goes. You can kind of tell better here. We're grabbing this number and we're pushing it into from here to here, that sorted list. So we're checking, moving, checking, moving, checking, moving, checking, doesn't need to move. Okay, move on to the next iteration. And then once you get to the end, then you're just done. You don't even have to check. You know for certain it's sorted. Quicksort, as you can tell, this is a bit quicker. Um, we're grabbing that pivot and we're checking all these, and until we get to here, none of these are bigger than a pivot, but once we get here, we get something bigger than a pivot. And then we check this. Oh, this is less than a pivot, so we move these. And it just continues on like that. And then you can see the second recursion, we split the list basically in half. And it just keeps going like that until it's done. It's really it. Pretty simple. A little weird to wrap your head around, but hopefully you enjoyed this, going over some sorting algorithms. Let me know if there's anything you'd like to see next Wednesday. Have a good day. Bye.